Hi everyone, I am Merve from Ericsson Security Research and this Turnet K11. Today, I will be presenting Monchai, a project focusing on mitigating uninitialized memory access in the Cherry Capability hardware architecture. Memory safety in software and industry is getting increasingly important, particularly due to the regulatory attentions. Memory safety means that every memory access must be valid. While there is no formal definitions, we can typically break it down into categories like special safety, temporal safety, or initialization safety. There are several ways to achieve memory safety properties. For example, using memory safe language like Rust, or applying static or dynamic analysis tools to code bases. More recently, attention has shifted to hardware-based solutions, particularly the Cherry Capability hardware architectures. Memory-safe languages requires rewriting old code to such languages. However, Cherry allows run legacy C and C++ code on memory-safe hardware. This makes Cherry particularly attractive as a practical path. In this talk, we will specifically focusing on initialization safety in the context of Cherry. The important question we have now, why does initialization safety matter? A programmer might declare variables but forgot to initialize it before use. This can lead to undefined behavior, non-deterministic bugs that they are difficult to debug. They can lead to security issues if previously allocated sensitive data is leaked. According to a survey by Herb Sutter, uninitialized memory access is the fourth most common memory safety issue after spatial, temporal, and type safety. Currently, Cherry hardware supports spatial and temporal safety, but not initialization safety. Our contribution is to extend the Cherry architecture to also provide initialization safety. Let me step back a bit and explain Cherry. Cherry is an instruction set architecture extension that replaces traditional pointer with the capabilities. These capabilities can carry metadata such as bound permissions that enable fine-grained memory protection against memory safety bugs that can cause vulnerabilities. However, Cherry capabilities are static. They don't change dynamically. To detect initialized memory accesses, we need the capabilities that are dynamic in the sense that they can gain certain permissions only after they have been used in this specific operation. To address this, our solution introduces conditional permissions. Permissions that are granted only if a prerequisite condition is met. These permissions follow the form X before Y, meaning that Y is granted only if operation X has occurred. On architectural levels, operations on memory are limited to load, store, and execute. Permissions on a memory are limited to read, write, and execute. For example, a write before read conditions means that only allow read access after a memory has been written to. But the conditional permission is more general. They can also express write before executes or other policies. For a single variables like a char, tracking initialization is simple. We need just a single bit. However, for arrays or larger object, we need to track which part of the memory region has been initialized. To solve this, we introduce operational bound. Operation bound works like this. At allocation times, the capability for that memory allocation is given only the right permissions. When a store operation occurs with that capability, the hardware increases the operation bound to precisely mark how much of that region initializes. Note that this is done only if a store happens adjacent to the current operation bound, so that bound can grow accordingly. We call capabilities with conditional permissions conditional capabilities. When the operation bounds reach the normal bound, the conditional capability has gotten the full possible conditional permissions and behaves just like a regular capability. The next challenge we have how to keep track of the additional bound. Since operational bound are not part of the standard capability, we have to extend the cherry capability format, include the operational bounds, encode in the last 16 bits of the capability address field. For more details, please see in the paper. With operational bound, we essentially introduce some state to the conditional capabilities. So, what happens when multiple capabilities point to the same memory? This would cause a problem with consistency of the operation bound across different capabilities. To ensure consistency, we introduce something we call sterilization pass to the LLVM compiler. This pass linearizes memory stores in LLVM IR, and by doing that, ensures that all capability referencing a memory region stay synchronized in terms of the operational bound. Our system is designed to be easy to adopt for developer. We support write before read compiler options and function level and variable annotations. And we implement automatic instrumentation pass. Firstly, a conditional permission pass instrument any annotated variables to enforce write before read permissions. Secondly, the sterilization pass ensures capability consistency automatically. We evaluated Monterey using the Juliet test suite on the QEMU system emulator. We focus on CWE457, use of initialized variable. Juliet has 560 good and 560 bad test cases for this CWE. Monterey successfully detected all the violation in the bad set. However, we observed 6 false positives, which still exhibit initialized behavior, but just not security relevant initialized accesses. We implement also Monterey on a Cherry RISC-V FPGA software based on an open source flute design. Compared to the Cherry-related flute core, Monterey has only 2% increase area cost. Also, we measure performance on the CoreMark embedded benchmark. Monterey incurs 3.5% overhead compared to Cherry Pure capability mode. To summarize, Monterey introduced conditional permissions and conditional capability for the Cherry capability hardware architecture. We integrate conditional capability into QEMU-based Cherry RISC-V simulator and FPGA-based Cherry-enabled flute core. We also developed full compiler support and 2 embedded memory allocator with capability support. Our evaluation shows that Monterey is practical with lower overhead. Thank you for listening. If you have questions, please reach us.